All right, ladies and gentlemen, thank you very much. As advertised, I'm John Randall. I'm very happy to speak with you at this quantum marketplace presentation, tell you about what Zyvex Labs may be able to do for you. What we provide is the highest resolution and precision lithography technology that's out there anywhere. We call it hydrogen depassivation lithography. It's actually a strange cousin to e-beam lithography done with a scanning tunneling microscope. It's automated, it's sub-nanometer resolution, and we provide atomic precision. If you're going to make quantum devices, you need some quantized energy states. If you want to create those, you can, for instance, create some quantum dots. We're going to take the example of 26 nanometer size quantum dots. The equation there shows a simplified calculation for the energy levels of quantum dots in a size D. So for 26 nanometer quantum dots, if you're going to go with semiconductor lithography, you can use EUV and produce 26 nanometer quantum dots. Unfortunately, the sloppiness of semiconductor lithography produces plus and minus 6.5% deviation in size, and that smears out the area where that first and second quantum state may be. With hydrogen depassivation lithography, HDL, it is much more precise, and the energy spread is tiny compared to what you can get with the current other lithography techniques. So this is hugely advantageous if you're trying to make complex quantum devices such as quantum computers or other complex solid-state quantum devices. Now, if you don't have the $250 million it takes to buy an ASML EUV scanner, you're probably going to use e-beam lithography to try to make your small devices. But we have a huge advantage even over the very best that e-beam lithography can offer. The yellow data is from a Carl Bergman paper from a few years ago. And the red is a model, but very well supported by experimental data for hydrogen depassivation lithography. It is just a ridiculously sharper tool. Now, it's also a relatively slow tool. An STM with a single tip is good for research, and as I'll point out, a number of groups are using it for research in quantum devices, but for manufacturing, we're going to have to significantly up the throughput. Happily, we were working to produce MEMS scanners as opposed to piezoelectric scanners, and in a paper we published a couple of years ago, we've shown that not inventing anything new, just doing some not trivial, but straightforward engineering, we can put something like 7 million STM scanners on a 300 millimeter wafer. And the STM scanners, being smaller, higher resonant frequencies, can scan at least 10 times as fast. What you're seeing there is an image showing atomic resolution imaging at 10 times the speed you can normally get with a piezoelectric scanner. Now, as I mentioned, this technology is currently being used to develop quantum devices. The list of places on the left are where our tools are sitting. There are other scanning tunneling approaches to hydrogen depassivation lithography. For instance, Rick Silver, our collaborator at NIST, is making analog quantum simulation devices with this technology. And you see a 2 dot and a 9 dot. It's roughly equivalent little dots of phosphorus dopants. And he's doing electron transport through there, showing strongly correlated electron transport, which is a great way to study Fermi-Hubbard physics and some other physics Hamiltonians in a way that you just can't do with cold atoms or trapped ions. We at Zyvex are also working on making ultra high performance 2D bipolar junction transistors that we believe will work very well in the cryogenic temperatures of a quantum computer backplane. If you want to get to higher precision faster, we've shown that we can make use HDL to make nanoimprint templates working with S.E. Srinivasan, at least proof of principle. Those should be able to make with a much higher throughput a wide variety of products, including quantum devices. I just want to leave you by saying that if you are making quantum devices, you will benefit from improved precision resolution. The picture here is to suggest that if you're using e-beam lithography, you're kind of stuck with more like the big paintbrush. With hydrogen depassivation lithography, a fine art paintbrush. Before I forget, we can also help you out with nano positioning issues if you have them. Let me end by saying that we are looking for development partners and investors. That's my time, ladies and gentlemen. Thank you very much.
Thanks a lot, John. So just a quick question. So in terms of hydrogen depassivation lithography, having 150x higher precision than semiconductor lithography, why is this capability so important for quantum devices?
Quantum devices are incredibly sensitive to size, unlike conventional CMOS, which is digital electronics and can live with very poor relative precision. Quantum devices, as I showed in the simulations, very small deviations push those quantum states around. I have experience in this back 20 years ago making quantum tunneling, resonant tunneling devices. And if you don't have just ridiculously good control of the features, you don't have control of the quantum states, which means you cannot make complex quantum devices.